All right, welcome back. We're going to talk about equilibrium a little bit. I know we started talking about equilibrium when we talked about reaction rates, but I'll give you a couple different ways to look at it still. All right, so if we look at, remember, equilibrium is a rate, right? So forward rate is equal to reverse rate. That's what equilibrium is. All right, so if you look at these two graphs here, and we think about rate, so this one right here is rate. So when we start a reaction, we have lots of reactants. And we have no products. So this is the start. Remember when we talked about rates, if you have a high concentration of reactants, it causes a faster rate because there's more collisions per unit time. Right, so if you think about it right here, right, so the forward reaction, the forward rate, is high at the beginning because we have a lot of reactants. And the reverse, right, so the forward's going this way, and the reverse is very small because there's not very many products. Right, and as the reaction continues, the reverse rate increases, and the forward rate decreases because as the reaction continues, right, we have a decrease in reactants and we have an increase in products until a time where the rates are equal. Right, when the rates are equal, then my arrows are equal. Right, and that's when we have equilibrium. Right, the forward reaction and the reverse reaction, if you look at this graph over here, are equal. So another way to look at that, so let me get rid of all this. Right, so another way to look at that is look at this graph right here. So amount of reactants, amount of products. At the beginning we have a lot of reactants, a lot of products. And at the end when we have equilibrium, right, you really have no relative change in the amount of reactants and products. But if you look at this reaction right here, right, that's favored over that. So for this one right here, you could say that the reaction favors products. That reaction favors products, or the forward reaction, because there's more products in the end than reactants. All right? So we talked a little bit about reversible reactions. Right? So reversible reactions, when there's reactants and products, exist in a state of equilibrium. Right? So things that, most reactions are this way. So most reactions aren't unidirectional. You don't have all your reactants make products. You have some reactants left and some products left. So we talked about the forward reaction. So products is forward. Reactants is reverse. And equilibrium, the rates are equal. Well, forward equals reverse. We talked about that. Equilibrium position describes where equilibrium lies. Okay? So if we look at our picture here, our two arrows, if my right arrow is bigger than my left arrow, right, this favors the forward reaction. So at the end, you have more products. Than reactants. If you look at this next one, my reverse arrow is larger than my forward arrow. So at the end, we have more reactants and products. And dynamic, right, means, well, actually, it's not. When we say dynamic equilibrium, it means that the rate So at that point, we have the same amount of product being formed as reactant. It has nothing to do with position. It has to do with rate. Okay, so dynamic means rate. All right, so equilibrium constant. You'll have to be able to calculate this. So the equilibrium constant is the ratio of products over reactants. All right? So it's the products over the reactants. Some important things to know here. Coefficients become exponents. Right, so if we take an equation, let's just take the simple water equation. So 2H2 plus O2 becomes 2H2O. So KEQ, K means constant, EQ means equilibrium, is equal to products over reactants. So if we think about it, product is here. The brackets mean concentration, so that's the molar concentration. But if we're doing a literal, so we're just using the chemical equation, I'll put my H2O here. And remember, my coefficient becomes my exponent. So this 2 here becomes my exponent. And on the bottom, I have my reactants. I have H2 and O2. My H2, remember, I had a coefficient of 2 here, so that becomes an exponent there. So this, my KEQ then, becomes that statement right there. Right, and then we can calculate equilibrium position. So this is really important right here. KEQ is greater than 1, it favors products. If it's less than 1, it favors reactants. Because if you think about it, I have products over reactants. So if I make more products than my reactants, it's got to be greater than 1 because it's in the numerator. If I have more reactants left, I have a greater quantity in my denominator. So this is really important. Give me a big star there. Right? So there's some complicated stuff with equilibrium, but we're not going to go into the complicated stuff because we're in distance learning. So maybe next year. All right, Le Chatelier. So Le Chatelier, super important guy. Right? So this guy made a statement. So I've shortened the statement down for you. It says the equilibrium of a chemical reaction to be altered by changing conditions. So basically what it means is this. If a change in condition is imposed at the system of equilibrium, it will shift that tends to reduce the change. Right, so if you look at our equation here, right, or before I do that, so here's a simple rule. If you add, so adding pushes reaction in opposite direction. So if I add reactants, it increases the rate to products. If I add products, it pushes toward the reactants, right? So adding reactants makes more products. Adding products makes more reactants. Okay, do you get that? So and vice versa. Okay? Vice versa. Alright, so removing, and I'm going to move this up a little bit. So removing pulls to what was removed. So if I remove reactants, it pulls to create more reactants. Right? If I remove products, it pulls to make more products. Right, so we have a simple situation in life. Right, so we have, I'll give you a practical, yeast plus sugar makes alcohol. Right? So by fermentation, if you remember biology, so alcoholic fermentation says if I take yeast and I give it sugar, it makes it happy, and one of its byproducts it makes is alcohol, right? And CO2. Right? So it makes a red rice. Right. So the problem is, at around 7%, somewhere around 7%, alcohol, the yeast dies because alcohol is toxic. It's kind of like if you just ate and you sat in a box and you filled yourself up with your own waste. Over time you would die because your waste is toxic to you. So alcohol is a waste from sugar metabolism from yeast. Right. So the thing is, we do this all the time, right? They make beer, mineral spirits. We use the CO2 to bake bread. So this is a common in our food and our beverage supply chain. It's a common reaction. But to be profitable, I don't want to simply just kill all my yeast and have to start over. Right? So how do I get my yeast to make more alcohol? Well, there's a couple ways we can do it. So Le Chatelier says, in order to make more product, right, I can do a couple things. I can increase the amount of sugar. So if I increase the amount of sugar, right, that'll push my reaction this way, right? So increasing pushes it toward the opposite. I can decrease the amount of alcohol. So alcohol is being made. Let me make these arrows a different color. So now if I remove some of the alcohol, the product, right? Oops, that is wrong. So if I remove it, it pulls it toward, right? If you think about it, I could also remove some of the CO2. So removing something pulls in that direction. Okay? So Le Chatelier said that. So if you look at this above reaction here, I got nitrogen dioxide, makes dinitrogen tetroxide, plus a decrease in pressure because I've decreased the amount of moles of gas, and an increase in temperature, so it's exothermic. So when this is at equilibrium, right, my rate of making nitrogen dioxide is equal to my rate of making dinitrogen tetroxide. So according to Le Chatelier, if I want to make more products, I can do a couple things. Right? I can remove this. I can increase the pressure. Right? So if this is a decreased pressure, the opposite is increasing. So if I increase the pressure, I'll pull it this way. If I cool it off, right, because that's the opposite of an increase in temperature, it'll also pull it off. So all of those will go this way. So I can remove N2O4. I can add pressure. Or I can remove temp. So all of those will make more products. If I want to slow the reaction down, I would do the opposite. I would add dinitrogen tetroxide. I would decrease pressure, right? Or I would increase temperature. So I can slow the reaction down that way. So that's what Le Chatelier said. Anyway, that's it for now, and I'll talk to you soon.